creepy screening here. There we go. Welcome back. So I have some cool stuff to show you today. Historically, in classes of non-quant students, this lecture usually goes off the rails a little bit because it starts to get sort of programming intensive. But I think among this group, you're going to love it. You're going to love it. And if I'm wrong, well, then so be it. I'm just enthusiastic. But I want to show you how to fit models within NL mixed specifically, but in general, how to be able to estimate any kind of model using maximum likelihood that either exists but doesn't have a package or that you make up your very own self. So this is a broader technique that I think should be part of your toolbox. That way you can implement anything that SAS doesn't already have built in or the analogous coding languages and other packages such as R and Stata. So the context why we need this is something called an exponential model. Have you worked with these before? A little bit? Let me show you a picture of where we're headed. So this is why we're going to need NL mixed. We'll talk about the model in just a minute. Here's an example data set of response time across trials where people are getting faster the more they practice. So this is one session within the data set that we've been looking at as our example. And the black line are the observed means. These are response times, so they are super noisy. But you can see the general trend. People improve rapidly, and then their rate of improvement starts to level off. So if we look at the fit of different models here, the red line is a quadratic model. So it does a good job of capturing the deceleration of change, but it predicts that they start getting worse again. So that's unsatisfying. A latent two-piece model I also fit to this data set, where the term latent means I let it figure out where the knot should be. I made that as a model parameter. If you want to see that code, I'd be happy to send it to you. Am I in your way, James?
No, you're good.
Okay, now I'll start using my mouse. Here we go.
I was just looking at the slide number.
Yeah, it's slide 36, sorry. In my enthusiasm, I forgot to tell you where we were. So slide 36 of lecture 6 is what I'm looking at here. The green line is the fit of a latent two-piece where it figured out that the best guess for where the knot should be slightly after trial 6, and it created a 2 linear slope model. And this one has a slightly positive slope actually for the second part. It gets closer to what I think is the more reasonable model theoretically, which is something called a negative exponential. So negative has to do with the sign of the change. It's change that's slowing down, so it's decelerating. That's where the negative comes in. A positive exponential would be a curve that sort of blows up. Like if you think of maybe bacteria growth in a sponge, like it expands, that would be a positive exponential. A negative exponential fit to these data is the blue line, where it has a parameter which is an asymptote. The value that is sort of the optimal level after infinite amount of time. So it explicitly predicts change that is expected to shut off at some point. Your level of your outcome at that point is a model parameter, as are individual differences. So this model, negative exponential, is non-linear in its parameters. It has e to the rate times time as a function, and so it's not something that can be fit in proc mixed or in any package where you have a linear model in the sense that it's slope times variable plus slope times variable. So to be able to do this, I have to show you how to use a package where you can write your own model. So I'm picking up here on slide 20, nope, not slide, page 25 of example 6. And given that exponential is a model that we haven't talked about yet, I figured it would be good to start with models that we have talked about, with which you're well familiar. That way I can show you how proc mixed and proc NL mixed map onto each other. So model 1B here repeated. This is our beginning step always. Empty means random intercepts. Only a fixed intercept says we have no change whatsoever. Random intercept says there's only individual differences in the mean, and we use this to compute an intraclass correlation. So if we look at the model, it has 3 parameters: fixed intercept, random intercept variance, and residual variance. Here's what this same model would look like using NL mixed. So I just want to introduce you to this procedure using a simple model, and then we'll add to it slowly to show you what it looks like when we get something that's more complicated. This is a way that you can estimate multi-level models of any kind. So NL means nonlinear. It requires you to write out everything that you want to estimate and to describe what the parameters mean via a set of equations. So the first thing that you have to do is what's given by this parm statement here. So again, SAS commands are in blue. Things that you would change that are specific to this data set or these variables are in black. And constants that you enter are in this sort of aqua color. So what I am doing here is naming and providing start values for the 3 parameters that I'm going to estimate in my empty means random intercept model. F int. Can you guess what I mean by that? Fixed intercept. Yeah. You could call it anything you want. You could call it Bob, or you could call it gamma 00. But naming it something that you will know what it means will make it a lot easier for you to follow your own code. On the second line, I have var u0. Can you guess what that one is? Random intercept variance, more specifically the variance of u0. That's what it means to me. And last but not least, var e. Yeah, the error variance at level 1. Where did the numbers come from? Those are starting values. They are helpful to provide, and then of course you're like, well, where do we get starting values from? In this case, I took them from the right answer. I took them from the results of proc mixed. Obviously, when you're fitting models that you don't know what the right answer is, this strategy is not going to help you. So I will show you an alternative way to come up with reasonable starting values by estimating the model in stages so that you get some of the values and as a good start for getting the rest of them. So these numbers came from the output that's down here. Next up, yeah, sure.
So choosing a proper starting values, is it more helpful to speed up the convergence, or it's more helpful to help it converge?
Both.
Ways?
Both. I have seen it to where if you put in the wrong starting values, it won't converge. It's also a way to check to make sure that you don't have any local optima. So if you put in different sets of starting values and you still come up at the same answers, that lends you confidence that you are actually at the maximum value. So yeah, it does help it speed it up, and sometimes it's absolutely necessary. It depends on what's in the model. For models like this, where it's a normal set of residuals at level 1 and a normal set of random effects, it doesn't need that much help. Okay. So next, I am writing out my multi-level model. So this part here is the level 2 part. Beta 0I equals fixed intercept plus this thing right here. This is going to be my individual random intercept, U0I. How do I know that? Because down here, I'm telling SAS what it means. I'm saying U0I is going to be a random effect. So this is the same thing as the random line that we're used to saying intercept, or 1 in R. See, I learned that this week. Yeah, see? 1, that's what I mean. More specifically, we are allowed to have different distributions for random effects. So I am saying that my random intercept is normally distributed with a mean of 0 and a variance of its random intercept variance. The level 1 equation without the level 1 residual is right here, is pred y. So that just has the beta 0I, the level 2 placeholder, and that's because the residual goes down here in defining the conditional distribution for my outcome, which is RT for response time. So we're saying that the distribution of response time is normal with a mean of whatever pred y is. So that means that pred y contains the fixed effects and any random effects. After controlling for the fixed and random effects, it has a variance of only level 1 variance. So that's why var E goes here. So then it works through this system of logic to figure out which of these things are parameters that we need to estimate. So that includes this fixed intercept. It doesn't include beta 0I. It doesn't include pred y because these are linear combinations of parameters. It understands that u0I is a random effect where what we care about is its variance, not each individual value. And estimate statements in NL mixed can be used for not only fixed effects but also variance components. Now this is super cool because it allows you to make linear combinations of variances in the same way that you would make linear combinations of fixed effects. For example, I'm asking for it to estimate the intraclass correlation as another new parameter that's a linear combination of my random intercept variance divided by my total. Now we get an ICC out of mixed already, right? What would be the advantage of asking for it this way? What do you think comes with it besides the estimate? Standard error, yeah. So this shows up as a very useful addition in certain contexts, such as when you're doing genetics analyses, where you're interested in trying to figure out variance components related to heritability versus unique environment versus things like that. They always want you to have standard errors and confidence intervals for those variance components, and this is one way that I know how to get them. The same thing can be done in M+ and a few other software packages, but this is super useful here to be able to get linear combinations of variances or fixed effects. Okay. Questions? So I'm just showing you the empty model so that you can get acquainted with NL mixed. The output is exactly the same. So the mixed output from the empty model is right here, where it differentiates the model for the variance, in which all parameters are listed under coparameter estimates here, and the model for the means, in which all parameters are listed under solution for fixed effects. In NL mix, it just dumps them together. So the output for NL mixed shows up in one table, regardless of whether it's a fixed effect or some kind of variance. And it's in the order in which you listed them on this PARM statement. So when we add to the model additional fixed effects, I'm going to list those all first, followed by the variances to make it easier for me to read my own output. The other thing I want to point out, in addition to additional estimates, so here's my intraclass correlation and its standard error. What does this mean right here? What's that? Not a trick question. 8546, what does that tell me? You can read the words next to it if you're stuck. What does it tell me? -2 times the log likelihood. So what estimator am I using? Regular maximum likelihood, not Remmel. Remmel does not exist in NL mixed. Remmel also doesn't exist in structural equation modeling programs. So this is a limitation. If you're trying to use this to estimate a model that is new or that you're inventing, or you don't know how to estimate any other way, it has to be regular flavor ML. That is why I showed you the poor man's version of exponential as a logged effect of, or a linear effect of log time last time. So in these, I have transformed mixed to use regular ML so that we get the same answers. One other thing I want to point out here, the output per parameter estimates in NL mixed has extra columns that you're not used to seeing. P-value is in the middle. So I'm used to looking at the end for the p-value. That's not there. It also gives you confidence intervals, and the very last column is something called gradient. Anyone know off the top of their head what that is? Or can read it off my notes here? Yeah, it's an index of parameter quality. It's the partial first derivative for that parameter. So you want it to be as close to 0 as possible, meaning it's really at the maximum value. The slope at the maximum is what this is printing. So this is all good. This is all good, meaning that it's 0 to several decimal places. Even though it will tell you the model has converged, it hits some sort of global convergence criterion, it is in fact possible for individual parameters to look crazy. So when you're fitting these models, you have to pay attention to not only whether or not the overall model hits some sort of threshold, but also each individual parameters. And if these things go crazy, that's a sign that there's something wrong. You may have put something in that doesn't belong there, or otherwise you have too much uncertainty to be able to estimate it. So that's a troubleshooting thing to try and keep track of. In terms of estimation, these are the options that I've specified. Given that it's just a regular mixed model with normal residuals and normal random effects, these don't technically apply yet, but they will once you get into more complicated models. Here is a convergence criterion for global. I changed this to a value that smarter people than me recommended in fitting these sorts of models. I'll just tell you that, it's completely arbitrary. Any guesses as to what the rest of this means? Yeah, these ones, yeah. This is method of estimation and technique of optimization. Newton-Raphson, and this is Gaussian Quadrature. So in models where you have a level 1 conditional outcome that's non-normal and a level 2 set of random effects, such as in an IRT model or a generalized mixed model, this is asking for full information maximum likelihood using quadrature. That, like I said, that doesn't apply yet, but it is, this is one way that you can troubleshoot things if your model breaks, is to go to something that's less intensive to get starting values and then go back to these more involved ways of estimating it. Estimation is not my strong suit, but there is a whole ton of documentation online that gives advice for particular types of models and which of these things will be more or less efficient. All right. So let's look at a slightly more complicated model. Again, something that we know how to do in mixed already, so it's just the NL mix that's new. Random quadratic time. So we did this one like a week ago, maybe 2 weeks ago. This is what the SAS code for mixed would look like. Here is the same model in NL mixed. So how many fixed effects do I need to estimate in a random quadratic time model? How many fixed effects related to the model for the means? I heard 3. I heard it whispered. It was you? What? Don't whisper. Say it loudly. You're right, it's 3. What are they? Fixed intercept, fixed time.
For linear and slope for the.
Yep, and so here they are. In the mixed code, you don't have to list this fixed intercept, it's there by default, but you can't forget it. So those are my fixed effects. According to this random line, how many random effects do I have? 3, right? An intercept, a linear slope, and a quadratic. So that means I need 3 variances and also my 3 covariances. So I have var u0, var u1, and var u2, as well as associated covariances. Again, starting values coming from the mixed solution. And then I also have a residual that has only variance components, a diagonal, with this on the diagonal here, var e. Here's my level 2 equations. So 3 placeholders, B0, B1, B2, each is defined by its respective fixed effect plus its random effect. Down here on random, now I've got 3. So now I need to fill out the means, variances, and covariances for my 3 random effects. All 3 means are 0. Why that is? The means of each of these distributions is already given by the fixed effect. The random is always how far off, so you expect a mean of 0. And then in parentheses is the G matrix in order of entry. So here's 1, 1, 2, 1, 2, 2, 3, 1, 3, 2, 3, 3. My level 1 model without the residual is right here. It's pred y. So now this is the conditional mean for each observation is a function of the individual intercept, individual linear slope, individual quadratic slope, where each person's individual effect comes from the fixed effect that everybody has plus the unique effect that is their random variant of it. And the model line then is the same. Response time is normally distributed with a mean given by whatever pred y is for each unique case and residual variance, a model parameter. So there's the mixed output where I have the G matrix, covariance parameter estimates, which is the G matrix listed out along with standard errors, fixed effects, and here is the NL mixed output. So note we hit the same log likelihood, that's comforting, and we end up at the same place with respect to all of the parameters as well. And my gradients are all very, very small, so yay. Okay. One trick that I've found to help speed estimation, or to make it more stable sometimes, is rather than estimating variances, is to estimate standard deviations. So in the models that follow, we're going to be following that trick and squaring the estimates to form the variances that they imply. Okay, questions so far? So you want to look at an exponential model? Why not, right? So now we know how we're going to estimate it. We're going to write it out. So negative exponential model is one example of what I would call a truly nonlinear model, meaning that it is nonlinear in its parameters, not just nonlinear in the variables. Do you know this distinction? So nonlinear in the variables means that you can have things like slope times time plus slope times time squared. The variables are nonlinear, but it's linear in its parameters because it's slope times variable plus slope times variable. This is not. This is different. There's 3 parameters in an exponential model. So I have figures to illustrate what they are uniquely for. So the big one, the reason we do this, is an asymptote. So in these models, the asymptote is going to be at the end of time. In other models, it might be backwards based on the pattern that you're trying to model. But it's the expected endpoint if time went to infinity. Where would you end up? What is the lowest value that your trajectory would have? And so these three lines were made by keeping the other parameters the same and varying the asymptote. So you can see that the red person ends up at a higher value than the green or the blue. Another is an amount. So both of these parameters are linear. They are outside the exponent. They are going to be easier to estimate. Amount is the total amount of difference between where you started and where you asymptote. It can be switched to become an intercept instead for the expected starting value if you want. But these three lines all end up at the same asymptote. They start out at a different place, and therefore they have a different total amount of how much they've changed from the beginning to the end. So amount or intercept, you can phrase it either way. The last one is the one that's inside the exponent that is the trickiest, and that's a rate. So these three lines have the same asymptote because they end up at the same place, and they have the same amount because the total amount of change is the same. They start at the same place, but they differ in how quickly they get to their asymptote. So blue has the most negative rate of change, meaning they improve at a faster rate. So when people say things like people have different learning rates, right, this is literally what they're talking about. So these types of models get used in studies of learning where we have literally rates to which you're hitting asymptote. And so each of these parameters then can have a fixed effect, meaning what happens for the sample on average, and random effect variation around it. So Belin, we are in lecture 6, slide 38. Excellent talk today, by the way. That was good. I want to talk to you about that after class if you don't mind, but just good job. So the name positive or negative refers to whether or not it's exploding or decelerating. So these are negative for these sorts of data. The amount is from the asymptote to where you began. So in this case, our amounts are positive because relative to asymptote, they started out higher. So amount is conceptually backwards because we're used to thinking about it as you changed, you went down, but everything is relative to asymptote as the reference point instead of intercept. So relative to where you ended up, what is the total amount of change? It's higher. You started out higher. You can get to what the intercept is by taking asymptote plus amount, so I'll show you how to do that as an estimate statement, and we need proc NL mix to do this. So if you look at the model here, level 2 looks exactly the same as what we did for quadratic models, as what we did for piecewise models. We have a fixed part for each of these terms and a random deviation from it. So how I know what the words should be for each of these parameter interpretations comes from the level 1 model. So that's where the trick is. That's where it's different than what we've seen before. Beta 0 so far has always been intercept. Now it's asymptote. It's where we end up after all of the change has taken place. And so where you end up on average is the fixed asymptote. How far off yours is the random. It's still an intercept-like parameter though because it's individual differences in some kind of level. Then we have beta 1, which is the amount of change. And here's the nonlinear part of the model. It's E to the rate times time. So it's a negative exponential model whenever with this gamma 2, 0, the fixed effect is negative instead of positive. Rules are the same in terms of number of fixed slopes. You would need at least 3 occasions to pull off this model and 4 occasions to have all of the parameters be random. Although I will tell you in practice, finding a random rate I have never actually done in real data. I have never had enough data to do it. The random rate is hard to find. And this may be an instance in which Bayes would help because you could put tighter priors or things like that to try and get better estimates of the random rates, but that's the part that's hard. It's the part that's inside the exponent that makes this tricky. So you want to give it a shot? Why not, right? You're here. So let's go back to the handout. I'm on model 6A, which is page 27 of example 6. So this first model has no random effects. I am fitting this just so that I can get start values for the fixed effects to then carry forward. So I have 3 fixed effects: fixed asymptote, fixed amount, and fixed rate. So I made up these numbers. Where did they come from? Well, asymptote. Asymptote is the amount of response time that we're ending up with after infinite practice. I know in these data what the mean is at the end. It's around 1600. So this is after session 6. If I let them keep practicing and practicing and practicing until forever, what is the best they could do? 1600. That seems reasonable. So that's what I put in as a fixed guess. Total amount of change relative to the 1600, they start out 300 to 400 milliseconds slower at the beginning. So that's how I put my start values here. Educated guesses from my data. Rate, I know it's negative because I know the pattern of the means. So -1 seems reasonable. The one I just made up, but I know negative. Now, changing the variance side here, I have only E variance. 600 is the standard deviation of E variance, which in this model is the only variance. So the total variance across occasions is the number that I took the square root of to come up with 600. And I know that from my data as well. So again, the entire purpose of this model is to get start values to run my next models with that are better than me just eyeballing my data and making shit up. So I have my level 2 equations without random effects. Pred Y is my level 1 model that looks exactly like I wrote it out in the slides. It's just an equation. So when people present equations in books or things and you think that model's really cool, I don't know how they did that. This is how you can do that. Response time is still normally distributed with a conditional mean given by Pred Y. And now, instead of saying the variance of the residuals, I put standard deviation squared. So it's still the same, it's just that the standard deviation will be a more stable parameter than a variance, according to Don Hedeker and other statisticians whose work I trust. Here are some examples of using estimates to get additional model implied parameters, such as where the fixed intercept is. It's the asymptote plus the total amount of gain. So I said before, you can replace amount with intercept if you want. And this is what the model says the predicted means would be according to what we have here. So I'm writing out the predicted means with which I can plot the predictions against the real ones to see how we did. Asymptote plus amount times e to the rate times time. How are we doing? Cool? All right, let's see how good my guesses are. Not bad. Fixed asymptote is 1675. Fixed amount is 284. I said 1600 and 300. Rate, I said -1. It's negative 0.67. SDE, standard deviation of the residuals, is 484. So I was off on that one, but it still didn't take very long. So it took just a few seconds to run this. But now I have better guesses for my fixed effects, and most importantly, the rate parameter to carry forward into the next model. Okay. questions, things you want to hear about again? So of my three effects here, asymptote, amount, and rate, I could decide to make any one of them random as a next step. I'm picking asymptote because level seems to be the broadest source of variation in these data, right? Intraclass correlation was 0.82. So most of the differences are due to mean differences. If I put in a random asymptote, that gets me to that same idea. Yes?
So there's not a hierarchy to the parameters?
Not in this one.
Okay.
Nope. I would argue that differences in level should always precede differences in some kind of slope, but I don't think that's strictly necessary. I just think it makes more sense that way.
Okay.
So, and knowing that there's a strong intraclass correlation, I would think asymptote would be first. So that's what I'm going to do. Add a random asymptote. So now my fixed effects have better starting values. And I'm making up some positive number for my random asymptote variance. So a semi-educated guess. Positive would be the important thing. Here are my level 2 equations where I've added a random asymptote. So U0I is what I'm using here. So notation is always specific to the model you're working in. If you didn't see the equation, what would you think U0I means? What has it always been? U0. Intercept, right? Not here. It's asymptote, because it's all relative to the rest of this, where this is the asymptote, not the intercept. So this model says people differ in where they end up, but they are the same with respect to how they get there. Parallel curves. So in this case, I'm also asking it to output the residual variance and the random asymptote variance by just squaring those standard deviations, so I can get it back onto the scale that I'm used to looking at the results. Otherwise, everything else is the same. So in this case, how do I know if my random asymptote variance is significant, if it helps the model? Any guesses? Even though you've never seen a random asymptote in your life, or maybe you have, but I'm guessing it. Well, how do I know if a random anything helps? -2 log likelihood. Yeah, same. And since we're in regular flavor ML, we could do likelihood differences, log likelihood differences, excuse me, to test fixed effects or random effects. So 8404 relative to my previous model of 9,000 and something, yes. Yes, we'll just say yes. I'll do that math in my head. Yeah, by the way, terminology thing. I've had students mess this up before. You can either say log likelihood difference, or you can say likelihood ratio. But you cannot say log likelihood ratio. Right? Does that make sense? I didn't know that, because that was one of those rules that I learned in high school that was gone by the time this came back. But if you have something where you have a ratio, if you take the log of both terms, then you're allowed to subtract them. So it's either a ratio of likelihoods or a difference of log likelihoods. Same way, if you multiply things and you take the log, then you can add them, which is why all of statistics uses log terms for the likelihoods, because people are supposed to be independent. You can add their log likelihoods together, and it's easier numerically than multiplying them. So let's do another one. I'm going to add a random amount next, because I think it's reasonable that the total amount of change that happens varies between people. So I am picking up two parameters, the standard deviation of U1 and the standard deviation of U01, which is another way of saying that the square root of the covariance. Try and keep everything on the same scale of square root. I picked up U1 in my amount equation for beta 1, and I picked up a second mean on my random line, as well as filling out my G matrix to 2 by 2. I'm asking for some extra stuff again. Of note, if I normally want to get correlations among my random effects, what do I ask for to get that? In R, it spits it out automatically. In other packages, in SAS, G-core in SAS, it doesn't happen in SPSS. And in Stata, it's RE covariance something. I forget exactly, but you can ask for it. There is no analog in NLMix, so I'm doing it myself. So I'm computing the correlation out of the covariance as an additional model parameter. So here are the parameters that were estimated directly in the first set here. Here were the additional parameters that I asked it to do. So strategy. Why did I do these first three? Any guesses? Did I need to do that? Is there anything like mathematically that I've gained? Nope. Do you know why I did that? Trail of breadcrumbs. So that when I look back at this 3 years from now, I will know what F meant. And so that all the parameters that I care about are in one place. This one table is all I have to save then, and everything has a nice happy label so I know what it means. Here's some random effects confidence intervals so that we could try to describe what happened. And then I tried to do random rate, and this is what I got. No. That's SAS for no. So I went to the troubleshooting online for non-convergence help. I tried to do a simpler method of estimation. First order something or another. I don't remember what FIRO stands for now. And no, wouldn't go. So either there is no random rate or I can't find it. One of the two. So we call it done. So here's how this model compares to our linear models, models from ProcMix that are linear in their variables or linear in their parameters. So random quadratic, there's that one. Piecewise slopes is that one, or that one, excuse me. This is the exponential. How do I know if this one's good enough? I like that it predicts something reasonable to happen after 6, but how do I know if it's good enough? Any thoughts? I've got two options. I could do a log likelihood test against saturated means. That works so long as you're in maximum likelihood, or I could do what we did in Remmel and add contrasts. Same thing on the variance side. Here is what each model predicts the variance to be at each occasion, where the right answer is the solid black line. So that's from the unstructured model. Random quadratic predicts the variance goes crazy. Piecewise slopes predicts it to be quadratic because each piece is linear. And my model here predicts that eventually the variance becomes constant. Does that look weird or does that make sense? Makes sense, right? Because everybody's done changing, right? They're at asymptote. So yeah, eventually the variance goes back to constant. How do I know if that's reasonable? The problem is, look at this. It seems reasonable theoretically, but it does a crappy job of getting to the actual part of the data. So this one is less satisfying, in part because it only has 2 random effects, whereas these other 2 options have 3. So they're more complicated and they're better fitting. There is no class statement by which to ask for session contrast, so I made my own. So within NL mixed, you can use conditional logic to make new pieces of data variables or otherwise execute if-then types of statements. So I created 3 new dummy codes for whether it was session 4, 5, or 6. Those are my 3 missing contrasts to get back to my 6 means. I stuck them in my level 1 model directly. So I have 3 new fixed effects, 1 for each of my new dummy codes. And last but not least, a contrast, a multivariate walled test, testing whether these 3 contrasts as a set are different than 0. So that's going to be an F. So the set of 3 contrasts are non-significant, which means my exponential model, this one, is not significantly different than these 6 means. Neither was the piecewise slopes model. The only one that was different was the quadratic. That one didn't fit. So I have 2 options in terms of model for the means that would be plausible to continue with forward. In terms of the variance model, I have to go back and get the unstructured model in ML so that I have something to compare to, and no, the variance model does not fit. So the exponential doesn't fit with respect to its random effects. It does fit with respect to its fixed. And so this is where I showed you, I think at the end of last time, the poor man's version of all of this. Writing out all of this is a giant pain in the ass. And you have to use ML instead of REML. So this is what you can do instead. Linear and quadratic effects of log transformed time look like exponential curves. So on the top 2 pictures, I have the original scale of time, and the curves are given by either positive quadratic, which is the red line, no quadratic, so this is a linear effect of log time, or a negative quadratic, and that one in particular looks a lot like what we might need. On the bottom 2 pictures, the x-axis is log transform time, so that you can see that the model that has no quadratic is a linear effect of log transformed time. So that was the last set of models that we looked at, and it would go through the same process. Here's a linear effect of log transform time against the means. You can add a random effect, tested the absolute fit on each side. It fit on the mean side, but not on the variance side. So this is the prediction of a random linear effect of log time in terms of the variances. You can see that it doesn't quite fit. And it's significantly different if you compare the predictions from that model to that of the unstructured. There's my p-value. So on that basis, I went ahead and added fixed quadratic log time. And yes, I had to get out Excel and figure out what the values of time would be on the log scale. So this is the point at which a 1 unit difference becomes a slippery concept, because it's linear with respect to log time, but it's nonlinear with respect to real time. But it is significant, so it did help the model, even though our model before was reasonably fine, and it does a much better job of approximating the variance side, which is actually the other side. Yeah, anyway, missing my picture. So yeah, those are that's the total set of comparisons of everything. Random quadratic log time wins on that. So. And that's why my handout is 41 pages long, because I'm trying all these things. So in practice, how would you choose amongst all of these various alternatives? Where do you even start? For every data set, do you build 41 pages of output? Probably not, right? But we know, based on studied design, what things would make sense. So let me get out Paint here. So do you remember this picture? I had group 1 and group 2. We talked about this last time. This is the treatment group, and this is the waitlist control. So I have 3 occasions. What if they had listened to me and added another one? So I have, that would be ideal. That's 2, this is 3, 4, and 5. There. If I have 5 occasions, I could have 2 random slopes. So if I know a priori that this is my design, we haven't talked about how to put group in the model yet. That's coming, because that's usually secondary to setting up your model for time. So what if all you knew is that you had 5 occasions, and then someone described that you had a treatment and a waitlist control? Would it make sense to fit, say, a quadratic model for time? You would end up with, if I tried to aggregate these 2 curves, it would be kind of like that, maybe? I don't know. That's the best of my PowerPoint drawing, or my paint drawing ability. If you picture these 2 curves, or these lines aggregating, right? It might look a little bit quadratic-y. Now, does that make sense in this context? If you know that this is where you're going to need to end up with respect to your testing. No. So, Ori, you have data where you have 5 occasions, right? Yeah. Are you going to fit a quadratic to it?
I hope not.
You hope not. So you started out by saying, well, I need to put time in the model, right? And you did. Linear time. How do you know if that's sufficient? Well, first question, do you have anything like this going on in your data?
No.
Where you have different groups of people doing different things at different times?
No.
Nope. Okay. So then so quadratic might be reasonable. But how do you know if quadratic is good enough, or if linear is good enough? Do you have balanced data?
Yes.
Okay, so you have an answer key. You've got 5 means, 5 variances, and 5 covariances that you can get back to as the right answer. How many people do you have?
3,000.
3,000. You have my permission to use ML.
Okay, thank you.
Now, are you off the hook in terms of design? Where do your people come from? Who are they? See, I already know the answer to this, so I'm setting him up.
Student.
They're students. So they're students who all go to the same school and have the same teacher. That's a big class, 5,000. No. Oh, so you have students nested in
Students in school.
schools. How many schools?
A lot.
A lot. How are the schools organized? Districts?
Yes.
Regions? States?
District.
Districts? Okay, so time, student, school, district. So then your question is not only is linear or quadratic enough for the means, but do kids need their own linears and quadratics? Do schools need their own linears and quadratics? That's the same thing as asking, is there a commonality in how students change if they go to the same school? Do schools, are they schools from the same district? Do they have a commonality in how they change? Are certain districts better than others? Right? And so your focus is on the random, not as much the fixed effect. These sorts of designs also come up in, have you heard of SMART trials? Sequential, multiple, adaptive, that's an acronym. These sorts of things come up in, let me get a new picture here. New picture, don't save. Something like this, where we have treatment and control schools, and they measure them for some amount of time, and then after that, the kids who have responded, we'll just call that a categorical thing for the sake of being easy, they don't need treatment anymore. So they go off and they do this, and we're going to measure them again. And of the students who did not respond, they are randomly assigned either to keep doing what they're going to do or do something else. And then these schools, control, have the same possibilities. The responders go over here and do this. The non-responders go over here and do this, and go in and do this. So we have two kinds of time, right? There's time, so this is a real design that I helped write a grant proposal of, where the treatment versus control was at the school level. So everyone in the school had the same thing happen to them. But response was an individual thing that could happen. So if you think about time in this context, there's sort of treatment time where something's happening, and then a break point at which the procedure changes, and something different is happening in phase 2. So this is another instance in which just fitting like a quadratic would be a mess, right? Because it doesn't capture the fact that there are two different epochs and two different kinds of dependency, right? Because what happened, whether you're in treatment or control, is a school level effect during this phase. What happened after getting each of these alternatives is a child level effect in the second phase. But there is still potentially dependency in that schools may differ in how many people responded to be able to go up here versus down here. So then you have differential weighting across all of this as well. So this is to say what happens with time depends on the sampling design very, very heavily. Only in cases where there's nothing that changes during the study in terms of the outcome, like the procedures, are continuous types of models going to be appropriate. Otherwise, you have to pay attention to what happens in each piece. And then try to have enough occasions to be able to track individual differences in change, which would be having at least 3 occasions on this piece and at least 3 occasions on the second piece. So, thoughts, questions?
So in this example, the piecewise regression data model.
I would either set it up as a piecewise model, or actually what I ended up doing is a set of 6 demicodes. Group 1, 2, 3, 4, 5, 6. That way, any comparison that I wanted, I could ask for as a follow-up of those means. So I put the intercept at the end because that was where they were interested in everything. And I had my 6 groups, and I had it set up so that these 3 groups have different slopes. Do you want me to write this out? Would that be helpful to see? Or do it talking is better? Yeah? Write it out? Yeah, it's... yeah, so this is my picture. Let me open up something here. So if I'm looking at the model, sorry, my notation's going to be bad here. Time within a kid within school. Actually, I take that back. I have written this out. One moment. I just have to remember the name of the person that I wrote it out for. Grant proposals. Have you seen these before? 15 pages of wall-to-wall text. This is a typical one, but this is what I'm talking about. There's their design. Words, 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 words. My section. Words, model. See, I'm like, I don't have to write this out. I've already written this out. So I'll walk you through it. Time within child within school. No IJK business. Letters that mean something. That's what I think, right? So now I have a series of dummy codes that turn things on or off. So I1 versus I2 refers to which phase it is, whether it's the first section of time or the second section of time. And I am using a combination of superscripts and subscripts to keep things straight. So I have treatment group or control group versus treatment group, where SRTS is one and SRTSG is another, where the G is the extra thing that they're going to be giving them. So if you look at just the first line here, what I have is for treatment schools during phase 1, an intercept and a time slope. Then I have for treatment schools during phase 1, an intercept and a time slope. Because at phase 1, that's all I know about these people, is that I've got this group and this group. And I set it up so that the intercept was at the end, because that's the point at which we're interested. The end of the first phase is where things get randomly assigned into the next phase. Then, the next line controls what happens to people who started out in this group right here. I have responders, non-responders, and the third group. I forget what happened. They get some extra special treatment. So then I have, if it's phase 2, and if they were in the first group, the control group, for people who were responders, who got allocated to the top line, there's their intercept and slope. For people who were non-responders, there's their intercept and slope. And people who were the third category, also non-responders, there's their intercept and slope. So I don't have a common intercept. What I have are intercepts and slopes for different people that are turned on or off based on which phase we're in. Dummy codes acting as switches, so that for a given row of data, your intercept and slope is only active if you're talking about that time period and that group. And then I have to follow it through in the random effects. So I have student level intercepts and slopes, and then, or those are school level, excuse me, and then student level. Ta-da! Now this looks hella complicated, right? It's not. That's it. That's the concept, piecewise slopes. What you're doing is allowing different slopes for different sections of the study, and then further allowing differences based on the design between treatment and control schools in the first part, and then follow up what happenings at the student level in the second part. So it's just piecewise slope models. I've seen papers where they try to reinvent these models in this context, and they come up with new words that aren't unnecessary. But yeah, that's all it is. So each of these slopes that I'm assuming is linear, but they could be nonlinear. And then I'm showing how to put it all back together again. So I gave, for each possible combination of people, how the model gives you their parameters. So during the first phase, this is control schools versus treatment schools. They are not differentiated yet. They get differentiated during the second phase based on whether or not they're a responder or a non-responder, and they're assigned to the two groups. And then down here, just to prove that I really knew what the hell I was doing, at least that was my hope, and that, no, we've thought about how the aims apply to this. Aim 1, did treatment work? Well, that's the answer. And do you know how I'm going to get this linear combination? Or how I got it for the power analysis I did? Estimate statements. Where W is a weight, because I have to re-marginalize these back together without knowing how many people are going to be in each of these groups, because it's going to depend on how many responders I am. And then aim 1, or aim 1B, was this. Does this cell work better than that cell more if it's this one than that one? That's 1B. And that's that linear combination. Or no, that was 1C, excuse me. So, point being, at the end of the day, these are just linear models concepts. Figuring out how time intersects and what kind of random effects needs to be there, that's the extra part that you're learning about right now. So, that one's easier. So you get a chance in your homework 6, which is available now, to practice 3-piece slope codings. It's a 3-piece model. But you're doing this version, the direct slopes, which is going to be much easier. So at the very beginning of the semester, I asked you guys why you were here, right? So if you had specific projects that you were working on with longitudinal data. Not Ori, you're Ori. I already picked on you. Ismail, you have longitudinal data that you need to analyze, right?
Yes.
How does that fit into what we've been talking about for strategies?
Ours is not. Before we were taking I was taking the class, I was thinking it was actual longitudinal, but as we go through the class, I realized that it's not real longitudinal because we just have 3 locations. One of them has 2 weeks between them, and the other one has 1 month later. I don't believe it's gonna fit much, but maybe the linear part is good, but I don't think we won't need the quadratic part.
So you have something you said that's 2 weeks. So like if you have time and then this is 1 month.
Yes.
So it's unequal interval.
Yes.
And you're expecting your outcome goes up or down?
We are trying to remove the effect of memorization because it has 5 personal assessment inventories in it, and we don't want them to, because we are trying to detect the fakers, or we are trying to remove the effect of memorization. That's the main purpose.
So you want them to score something like that, where at the second occasion they would remember the test and do better, and they would have forgotten by the end?
Yeah, kind of.
Kind of? So in your case, if these are different processes, enhancement because of memorization and then decay, that would argue against a linear model, right? You would expect, I mean, depending on whether or not you have enough precision here to capture it, it seems like that would be potentially 2 slopes instead of 1. If it's 1 process, then 1, then the key is just making sure your time variable reflects what a unit is, because this unit is not the same as that unit. But it is longitudinal. I mean, even data that's collected over seconds is longitudinal. The question is whether there's systematic change, right? And with only 3 occasions, how many random slopes can you test? 1. 1. Yeah, next time get 4. Yeah.
It is very hard to keep people with 304 items.
Ah, that is a whole separate problem.
Yeah.
Yeah, I can't help you with that one. How about you, James? What kind of data do you have?
Like the ones that I showed you?
Well, that's 2 occasions. That's yeah. Do you have any other longitudinal data you care about?
I mean, I guess the actual data that, the actual MRI data itself is longitudinal. We collect a new data point every 2 seconds.
Yeah, so that's super longitudinal.
So, yeah, with that, we're essentially measuring a proxy of neural activity at every 2-second interval, and then dispersed through that, say, 600-second run, there are certain events that occur that we would like to model.
So then, like, they're watching something or they're doing something, and then beep.
Yeah, then then there's usually some task that's being presented. Say they see 5 arrows on the screen, and they have to respond to the direction of the central arrow and ignore the directions of the flanking arrows.
Yes.
So that occurs from, and at the other times they're just staring at a white cross.
Posner task? Is that?
We call this one the flanker.
The flanker, yeah. This
So
is
it might
bringing
be-
back that used to live in that world a little bit. So then you have a lot of measurements every 2 seconds, like while they're doing these things,
So
or just they're doing that over and over again.
yeah, we have it split up or dispersed. So I guess a lot of the time there'll be random periods, and maybe it's just 4 seconds of them just looking at a blank cross before they see the arrows. Maybe it'll be 10 seconds. Maybe it'll be 14 seconds.
That way they don't know what's coming.
Yeah, so there's a little bit of things that can't be anticipated.
So before the cross and after the cross, that sounds like a piecewise model to me, right? Yeah. So if you know when they appeared, then you know how to segment things. So yeah, they show up as very useful. Anyone else want to play? We're going to be done. Yeah, we're done. All right, well, I'm happy to answer questions at any point if you're thinking about how does this apply to you, because it can be daunting when you approach a data set to think, where do I even start? But start with the design, start with what makes sense, then look at the means to see where you should go. And so we're going to do a little review next time to try and recap what we've learned, and then take a slight different direction into a tutorial on interactions, because when we get into time invariant predictors, everything's going to be an interaction of some kind. So I'll need to make sure that you can do that. So.
Actually, there is another data that I'm collecting, but it's not with the research group that I have. I'm doing it on my own because I'm trying to create an achievement goal framework questionnaire, and it aims to measure the attitude towards their students' self-esteem about mathematics and how they do in mathematics in real. And in 10 months school, every 2.5 months, same people are getting the same measurement too. And what I'm expecting is at the beginning of the year, I believe that they will be much more motivated, and it will increasingly decrease by time at the end. And I'm trying to prove that, but I'm still waiting for the 4th batch of the data at the end of May.
Well, that line that you just did, that's exponential.
Yes. That's
So,
what I'm expecting.
yep, now you know how to do it. So, good. All right. Well, then I'll see you Thursday. Office hours start now. Have a good day.